Okay, folks, we are back talking about permutations with repeating objects. A set of n objects with A of one kind that are identical, B of a second kind that are identical, and C of a third kind that are identical, and so on, can be arranged in this many different ways. And factorial divided by A factorial, B factorial, C factorial. Okay? Let's do a quick intro to illustrate. Consider the three-letter word cat. How many three-letter permutations are there? Show this using the permutation formula. So the order matters. I want different arrangements of the letters CAT. So I'm taking three letters. I'm permuting them three at a time. 3 factorial divided by 3 minus 3 factorial equals 3 factorial over 0 factorial. Remember, 0 factorial is just 1, so 3 factorial is equal to 6 different ways. Or fundamental counting principle. First letter, 3 ways, 3 choices, sorry, times second letter. I have 2 left. I don't want repeats, right? No repeating the letters. Times 1, I get 6 ways. So I have CAT, CTA, ACT, ATC, TCA, and TAC. Oops. TAC. Those are the 6 ways. If we change, so part 2, if we change the A in cat to a T, we get the word CTT, which has 2 letters which are repeating. So let me just rewrite the 6 choices above. Okay, and as they said, I'm going to change the A to T. So all the A's I see, I'm going to change to a T. Okay, there we go. How many different arrangements of CTT are there? Well, here's one. This one is the same, so I'm not going to count it. That's a repeat. Here's another one, TCT, but this one's a repeat. Not going to count it. Another one, TTC, another repeat. So now I have 3 different ways using this new formula for permutations with repeats. Okay, CTT, 3 letters. I can permute CTT in 3 factorial ways, but I have T and a T, 2 repeats, so 2 factorial. So I can say A equals 2, therefore A factorial is 2 factorial. Okay, so that is equal to 3 times 2 times 1 divided by 2 times 1, and I have 3 ways just like we counted. Okay, and this is when there are repeating numbers, repeating letters. Okay, another example. Determine how many different 11-letter arrangements you can make using the letters of the word Mississippi. Okay, Mississippi. There are 11 letters in all. 11 letters total. Okay. Letter I repeats how many times? 4 times. Letter S repeats 4 times. And the letter P repeats how many times? 2 times. So that is 4 factorial, 4 factorial, and 2 factorial. Okay. So the formula, n factorial over a factorial, b factorial, c factorial, 11 total arrangements, so 11 factorial total arrangements, divided by, let's divide out, it's like you're dividing out all the repeats. 4 factorial, this is for the repeat of the i's. Another 4 factorial, that's a repeat of the s's. And another 2 factorial, that's the repeat of the letter p's. And on your calculator, you do this, the result is 34,650 different ways. So 34,650 different 11-letter arrangements of the letters from Mississippi. Okay. Okay. Next example. In how many ways can you walk from A to B in a 3x4 rectangular city if you must walk on the grid lines and move only up or to the right? So if you remember from way back, lesson 1, remember this? Right? We had you guess how many different ways you thought. Now let's actually calculate it. Instead of actually sitting there and trying to figure out every single path and writing it all down, okay, let's think of it logically. And this is a permutation problem with repeats. So from A to B, okay, it will require 3 ups and 4 rights to get to B. No matter what path you choose, as long as you're moving always closer to B by either moving up or to the right, you will have to go up 3 times and right 4 times. So this is one of the paths you can do. Up, 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 right, 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 right. So up, 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 right, 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 right. Okay, to get from A to B. Let's think of this as a permutations with repeats problems. This fictitious word, U, R, how many different arrangements are possible? If you figure out how many different arrangements are possible, you figured out how many different paths are possible from A to B. 7 letters. Okay, there are 3 U's, 4 R's. Divide out the repeats. 3 factorial, 4 factorial. 7 times 6 times 5 times 4 factorial over 3 times 2 times 1 times 4 factorial. Cancel. Do all the math there. I get 35 different paths. Okay, and if you want to sit there and try to figure out brute force, count them all out, see if you can get 35. Okay. Right. I'll give you a moment for this you try. Okay. How many, determine the number of permutations of the letters of the word mathematical. Pause here, give it a try, and then come back. Okay, so, all right, we're back. So 12 total letters in mathematical. M, there are 2 of them. A, there are 3 of them. T, there are 2 of them. So if I set up my formula, 12 factorial, total number of letters, or total number of arrangements, 12 factorial, but I need to divide out all the repeats. So for the M's, it's 2 factorial. For the A's, it's 3 factorial. For the T's, it's 2 factorial. I get 19,958,400. So it's important to stop here and think about what does this number mean. Okay, this is the number, okay, of different, that's the key, number of different arrangements of the letters in mathematical. Okay, it's important to stop here and think, right? What do you mean by different arrangements of the letters mathematical? So if I have mathematical here, okay, the reason we divide out, let's just take an example, the letter M, there's two of them, right? They're the same letter. So if I swap the position of this M and this M, I still get the word mathematical. Okay, but we don't want to count, don't count both cases. Okay, how do we not count both cases? We divide out by 2 factorial to take care of the fact that there are these two cases of mathematical. Okay, when you swap the M's, it's still the word mathematical, but we don't want to double count. Okay, so this prevents double counting. All right. Okay, next one. Cereal time. Ahmad bought a carton containing 9 mini boxes of cereal. There are 3 boxes of cornflakes, 2 boxes of Rice Krispies, 1 box of Cocoa Pops, and the remainder are Raisin Bran over a 9-day period. Lots of cereal. Ahmed plans to eat 1 box of cereal each morning. How many different orders are possible if Ahmed eats Raisin Bran on the first morning? Okay. Let's see. So, first morning. Well, let's do this. Cornflakes. Let's just abbreviate. CF, Rice Krispies, RK, Cocoa Pops, CP, Raisin Bran, RB. Okay, there are 3 CFs, cornflakes, 2 Rice Krispies. Let's see, 1 box of Cocoa Pops, CP. Let's see, and the remainder are Raisin Bran. So 3 plus 2 plus 1 is 6 remainder, so 3 have to be RB Raisin Bran. Okay, so there are a total of 9 boxes. The first box must be Raisin Bran, but think about it, there's 3 boxes of Raisin Bran, so I have 3 factorial ways to choose a box of Raisin Bran, right? But whether you choose one Raisin Bran box or the other one, is the same cereal, so I need to take care of the repeat. So it's 3 factorial divided by 3 factorial, which is 1, right? So it shouldn't matter which box you pick so long as it's Raisin Bran, because you have 3 choices, times the rest of these 8 boxes. That's 8 factorial divided by, okay, now you want to think about the repeats. Now there are only 2 left, right? There's 8 boxes. So divide out the repeats. So cornflakes, Rice Krispies, okay? And then the last one is the remaining Raisin Bran. Okay, so that all of that is 1 times 1,680. So 1,680 different ways to eat the cereal. Okay, next page. Permutations with restrictions. When you encounter a situation with constraints or restrictions, always address the choices for the restricted positions first. Example, using the word orange, determine how many arrangements are possible using all the letters if the letter A must be first. So whenever we have these word order things, right, I'd like to chart it out like this. So the very first letter must be an A. And I draw a line to say that the rest of the letters are not restricted. Yep, so orange has 6 letters. The first letter must be A. So how many ways? Okay, so how many ways can we select the letter A? Just one way, just one A. Okay, and then the rest of the letters. Okay, so A, and then the rest are going to be O, R, N, G, E, right? You have 5 choices. Okay, we want possible different arrangements, so 5 times 4 times 3 times 2 times 1. So there are not going to be repeats. So 1 times 5 factorial equals 120. Or we can think of it this way with permutations, right? For the letter A, it's one letter taken one at a time, which is just 1, times 5 letters taken 5 at a time. So this is O, R, N, G, E. Okay, and do all the math there, and you're still going to get 120. Oops. Right, example 2, using the word formulas, determine how many arrangements are possible using all the letters if the letters OR must be together in that order. Okay. Let's see, OR has to be together. Let's do this. Let's treat OR as like one package, like it's together, right? I know it's 2 letters, but let's think of it as like a single entity, OR, so that it's got its own positions. So in formulas, there's 8 letters, but since OR has to be together here in that first position, actually, let me take that back. The OR, I'm going to start off with saying it's in this position, and we'll talk about the rest later. Let's start off with OR in this position. The 2 letters are acting as like one letter together since they must be together in that order, so that the rest of these letters, there's 6 remaining letters. 1, 2, 3, 4, 5, 6. This is going to be the letters F, M, U, L, A, S. Okay? Let's think of it this way. I essentially have 7 different entities. So this is 1, 2, 3, 4, 5, 6 letters here. Okay, 6 letters there. And then I have a 7th kind of letter or entity there. So how many different ways can we arrange these 7 things? So OR, so 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so if we think about this, an example would be ORFMULAS. Okay, one of the things I find helpful with permutations is that doing the calculations, understanding how to do this is one thing, but if you don't get the conceptual, like the abstract part right away, do a couple of examples like I'm doing here. So one way I can arrange it is like this. Another way, the OR has to stay together, so it could be like this. Oops. Like that. Or like this. Okay, notice with this example, I'm just varying the position of the OR, but all these other letters can also change position, but I'm just illustrating that this OR changes position, and there's 7 different places it can go, right? So it starts with a 7, and then so on, 6, 5, 4, 3, 2, 1. So it's like 7 factorial. Okay, so 7 factorial, do that on your calculator. You get 5,040 different arrangements. If you're looking at notation for permutations, so you can say 7 things, permutation of 7 things taken 7 at a time, do that on a calculator, you'll still get 5040, 5040. Okay, All right, next one. The letters MRA, so still the same word, formulas. The letters MRA must be together, but not necessarily in that order. Okay, MRA. So let's map it again. So I have MRA, and then I have how many letters remaining? So that's 5 letters. 1, 2, 3, 4, 5. And then what are those letters? F, O, U, L, S, right? So if I'm looking at this, okay, what do we got here? So if we keep the MRA, kind of like an example with this OR, if you keep the MRA as one block of letters and it moves around, there's 6 times 5 times 4 times 3 times 2 times 1 combinations of MRA and FOULS. So to demonstrate, MRA, FOULS, FMRA, OULS. Okay, so FOMRA, ULS, and you can see that the MRA block is staying together. Okay, but also consider that all these other letters are moving around as well, and that's accounted for with the way our factorial is set up. Okay, so this gives us 6 factorial, but let's keep in mind it says must be together, but not necessarily in that order. So MRA can be permuted, right? 3 things, taken 3 at a time. MRA, the arrangement of letters MRA can be permuted 6 different ways. So I have to multiply by 6 because as the MRA moves around, right, and all the other letters move, that MRA can also be RAM or MAR. And that's accounted for with this 6. Okay, so 6 factorial times 6 is 4,320 possible arrangements. All right, example 3. 5 starting players, Anne, Betty, Claire, Denise, and Ella from the basketball team are sitting on the bench waiting for the game to begin. Determine how many ways they can be arranged if Ella is seated in the middle. So I'm going to abbreviate these names. A, B, C, D, E. 1, 2, 3, 4, 5. Okay. I'm going to do this with the fundamental counting principle. Ella is seated in the middle. So Ella, only one choice, right? One way you can do it. Ella is just Ella, one Ella. The other 4 seats, no restrictions. Okay, so this is Ella. The other 4 seats, no restrictions. So 4 players left. So 4 times 3 times 2 times 1. Okay, so 1 times 4 factorial, or 24. Or if we're using permutation notation, the permutation of one thing taken 1 at a time, that's Ella's seat times 4 things taken 4 at a time, and that still is 24. Anne and Betty must sit together. Okay. Let's see. So this is Anne and Betty. And then this is CD. Oops. Anne and Betty. And then 3 more seats, right? C, D, E. Anne and Betty, right? So if I take A and B, just like our example with formulas and orange, right? Sorry, with formulas, with the OR and the MRA, this AB considered as one block. So there's 4 times 3 times 2 times 1 arrangements. But AB can be permuted in two ways, right? Two things taken two at a time. So the permutation of two things taken two at a time, and that equals 2. Okay, so that ends up becoming 4 factorial times 2. Oops. Times 2. And that equals 48 different ways. Okay, Ann and Betty cannot be seated together. Okay, this one's a bit trickier. But instead of trying to map this out like this, where it's like, okay, Ann and Betty, oh, they don't like each other. They can't sit next to each other. There's one case, right? Here's another one. Here's another one. Man, it's going to take too long, right? So no. Okay, let's think of a smarter mathematical way to do this. Okay. Find total number of ways for seating, no restrictions. What is that? One, two, three, four, five, 5, 4, 3, 2, 1, right? Or just 5 factorial, that's 120 ways. Number 2, A and B seated together, 48 ways. We just calculated this, folks, right here, 48 ways. Okay, so if I subtract 1 minus 2, I should get number of ways A and B not seated together. Makes sense, right? Let's see. 120 minus 48, and that's 72. This is a smarter way to do it. You can do, this thing for a whole bunch of different cases and start lining it up like this and then figuring out the numbers here. But man, that takes too long, okay? Usually this is a nice little trick where you find no restrictions case and then find the analog or the inverse of the restrictions case for the particular case, like here, how many ways they're seated together. Then you subtract and you end up getting the answer that you want where it's not seated together, okay? Next page. Permutations requiring cases. Determine how many here we go. Sorry. Some problems have more than one case. One way to solve such problems is to establish cases that together cover all the possibilities, calculate the number of arrangements for each case, and then add the values for the cases to obtain the total number of arrangements. We kind of saw that in a previous example, I think last lesson, with that case-by-case analysis of the even number starting with 0, then the even number problem starting with 2, 4, 6, 8, right? Or the 3-digit number, 2-digit number, finding the 1-digit number and less than 300, then adding them all up, right? So let's do a couple cases here. First, start out with determine how many 4-digit odd numbers you can make using the digits 1 to 7. So 1, 2, 3, 4, 5, 6, 7. If the numbers must be less than 6,000. Okay, 4-digit number. So this is 1, 3, 5, 7. So there's 4 possible cases here. Okay. Another restriction. I have 5 choices here because must be less than 6,000. So that first digit cannot be a 6 or a 7. It has to be 1, 2, 3, 4, and 5. So I have 1, 2, 3, 4, 5. I have 5 choices. Okay. Okay, it says it doesn't say repeats are not allowed, so repeats allowed. We've dealt with our two restrictions here and here. So I can put any number of 7 digits in the last two slots there. Okay, 5 times 7 times 7 times 4 equals 980. Okay, here's where the cases come in. The numbers must be less than 6,000 and no digits are repeated. Okay, case number 1, even number first. If my number starts with an even number, that's going to limit the number of choices for the last digit. So if I do 1, 2, 3, 4, okay, even numbers first. Okay, I only have two choices, 2 or 4, because if it's 6, that's over 6,000. I need to be less than 6,000. Okay, so 2 or 4, I have two choices. And because of that, right, for the odd number in the back, last digit, I have 1, 3, 5, 7. I have 4 choices. Okay, no repeats. If I've used 2 digits here already, 7 minus 2, I have 5 choices here, then 4 choices here. Okay, that is 160 arrangements. Or case number 2, odd number first. Okay, so if an odd number is first, 1, 2, 3, 4-digit number. Okay, 1, 3, or 5, I have 3 choices. And I can't pick 7 because it has to be less than 6,000, right? So 1, 3, or 5. Okay, here's where the difference comes in. There's a 4 here, right? There's a 4 here. This one, I have a 3. My choices are 1, 3, 5, and 7, less one number because of first digit. Okay, this is why the cases are important. Okay, and then this is the same as the others, right? 5 times 4. Okay, and then that is 180. 340 possible choices. Okay, challenge, last one. Determine how many arrangements of the word Alabama there can be with the following conditions. Wow, these US states have lots of repeat letters. Okay, 7 letters. Okay, must start with exactly one A. So A. Oops, let's do this. 1, 2, 3, 4, 5, 6. So must start with A. Okay, and then this one, Alabama, are the remaining letters, 6 letters. Okay, there's only one way to choose A. If we're getting super technical, there's actually 4 ways to choose A, but we don't want to choose it all the same way, so we have to divide it out by 4, and that's really where you get the 1, right? Okay, and then arranging these letters, 6 times 5 times 4 times 3 times 2 times 1. Okay, but be careful, I have 3 A's, so let's write this out. So 1 times 6 factorial, but I have 3 A's, so that's divided by 3 factorial. Do the math there, I get 120 ways. Okay. Must start with exactly 4 A's, so A, and L, B, M is all that you're left with after you take out the A's. Okay. How many ways to choose 4A's? Well, there's exactly 4A's in Alabama. Okay, there's only one way to do that. Okay. And then LBM, there's 3 letters times 2 letters times 1. When you're making choices, okay. Okay, so how many different arrangements? So that's 1 times 3 factorial, and that equals 6.